All right, in this video we're going to talk about a concept called hybridization. Hybridization is a mostly theoretical concept that kind of is trying to explain what's happening to the orbitals in bonds as they're forming, and it's a hybrid between what we expect from VSEPR theory and something called valence bond theory, which I haven't even introduced yet. Valence bond theory is not great. This concept that I'm about to talk through is relevant and it makes sense and it works really, really well. But in practical application, this falls short almost immediately. So we're going to take this tiny little part of this theory and combine it with what we can predict from VSEPR theory and kind of try to explain what's going on. So valence bond theory is trying to explain what is happening in a covalent bond. So we said, when we have a covalent bond in a Lewis structure, both sides put in one electron and you draw a line. Yay, shared electrons. This says that a covalent bond is formed from pairing of two electrons, so each of them donate one electron, and they have to have opposite spins. So you remember when we talked about orbital diagrams that there had to be up arrows and down arrows? So the idea is each of them is donating one electron, and as long as they've got opposite spins, we're good. And then there's a region of overlap of the atomic orbitals between the atoms. So between the atoms, like if you have a p orbital here or an s orbital here, the overlap of those and each of them donating an electron with opposing spins is what causes a covalent bond. Great, we're gonna run with that idea, sounds perfect. So in terms of visualizing it, sometimes it's written like this. So for something like hydrogen, hydrogen would basically, if you have two hydrogens, they both have one s orbitals, and typically they would both get an up arrow, but in order to form a bond, one of the reasons it takes a little bit of energy to form bonds is that you have to rearrange how the electrons are organized, so we would have one up and one down, okay? And the idea is these would come together and you would form a 1s orbital that's got both, and it applies to both hydrogens. Okay, this would be one way of visualizing a covalent bond with valence bond theory. Okay, some people visualize it more about the shape, and we're going to do that a lot with hybridization. So an s orbital, if you remember back to the shapes a couple chapters ago, should be a sphere. And this is still a 1s orbital, and the idea is they would have each of them would have one s orbital, and when they combine, what you would end up with is essentially, it's an overlap of those orbitals. I did not draw those even remotely symmetrical, sorry about that. It looks like a Venn diagram, but the idea is that overlap is what causes the bond. Whichever way makes more sense, we're gonna kind of use them both. Visually, this is probably more correct, but there's nothing wrong with thinking through it like this. Okay. So the problem is that valence bond theory sounds great, but it predicts horrible bond angles. Like none of the bond angles agree with VSEPR theory. So we're going to take just this basic concept from valence bond theory, and we're going to talk about something called hybridization. Okay. I know the last page had hybridization at the top. It's kind of the title of this section. So, for example, so this is basically making valence bond theory, which is not great, and VSEPR theory, making them coexist. You kind of get different answers depending on which one you use. So for example, if you talk about carbon, okay, coming back to orbital diagrams here, you would have helium, 2s2, 2p2. Up arrow in each of those. And the idea is that based off valence bond theory, okay, you need to have unpaired electrons, right? Because you have to have unpaired ones to be able to pair up to make the bond. Unpaired electrons can make bonds. Well, according to this, we have 2 unpaired electrons, so we should expect 2 bonds. And we expect them to be 90 degrees apart because if you remember way back to the geometry of p orbitals basically have, so I guess I'll draw this off to the side here. Try to draw them in different colors, how about that? If you have 3 dimensions going on here, okay, you're gonna have 1 p orbital above and below the z-axis, you'll have 1 on the y-axis, and you'll have 1 on the x-axis. Pen's kind of dying, but whatever. Okay, but the idea is they're all 90 degrees apart. Well, this is completely wrong. We know this is not right. So this is where valence bond theory fails almost instantly. So, in all actuality, you get 4 bonds at 109.5 degrees, the tetrahedral, okay? So there's a discrepancy between VSEPR theory and valence bond theory, but experimentally we know this is the right answer, so valence bond theory is the one failing here. But the idea of unpaired electrons overlapping to form bonds is a really useful way of visualizing this, okay? So one thing we can do is we need to understand that, yes, this is the default answer for the orbital diagram for carbon, but in theory, these electrons can be moved around. So one of the first things we're going to do is we can take this and we can actually move the electrons around to get them more evenly distributed. I'm trying to draw the boxes bigger so I can point at things better. And essentially what we need is 4, we know we have 4 bonds, so we need 4 unpaired electrons. Well, this one's paired, but we have an empty space for it. If we just move this one over here and unpair it, so essentially this electron came over here, we now have 4 unpaired electrons. And I'm fully aware that at first glance you're like, why would that make sense? Why would you do this? And this is where hybridization doesn't have a great backstory. We're doing it because it works. Okay. So the problem is we can get 4 bonds, but we still don't expect that 109.5 degree angle. Okay. At this point, if we started from here and we still used valence bond theory, we expect, like suppose we had CH4. Okay. Simple tetrahedral, simplest tetrahedral I can think of. We would expect the hydrogens to all have s orbitals like we saw in the last page, s orbital. And this has an s and 3 p's. We'd expect 1 s to s bond and 3 s to p bonds. So this is from hydrogen, this is from a carbon. I guess I'll label everything hydrogen, carbon. So in other words, the way we could visualize it is if the hydrogen had an unpaired electron, it doesn't matter which one gets flipped to be upside down, but the s orbital from the hydrogen could pair up with the s orbital from the carbon and form a bond. Great, and it would be an s-s type of bond. We could also expect the s orbital from the hydrogens to pair up with the 3 different p ones and form 3 different s-p bonds. And the problem is these are all going to be a little bit different. The problem is experimentally, all 4 bonds are identical. There's none of this SS and SP stuff. It's all exactly the same. So we have to account for that. We have to explain how this works. So hybridization is entirely theoretical, but it seems to work really, really well, so we're going to keep doing it. Okay. So I guess I've said it a couple times, but I haven't written it in the notes. Hybridization is a theoretical process, or let's go with hypothetical process. Okay, it's basically a mathematical way to explain the discrepancies between the two theories. Okay, it's generally thought of as switching from atomic orbitals to molecular orbitals, or hybrid orbitals. So atomic orbitals, which are sp, d, and f, to bonding orbitals or molecular orbitals, usually they're referred to as hybrid orbitals. And this is essentially where the valence bond theory fails. So the idea was back here with valence bond theory that it's like, okay, even if we unpair things to make 4 bonds, we still have an s and 3 p's, and we know that that's not the case. The idea is that these orbitals are changing when they form bonds. They're no longer just atomic orbitals. Okay, so let's look at CH4. The process on this is a little weird, but it's not super difficult. You just have to kind of learn to deal with it. Okay, so in terms of plotting things versus energy, which we don't usually do, I don't know why I drew that diagonal, sorry. Starting from this point, because we know we need 4 unpaired electrons, the s orbital is only going to have 1 electron, and it's going to be lower in energy than these 3. So we have a 2s with 1 electron, and we have the 2p, which each has 1 electron. And the idea is these 3 atomic orbitals mesh together because they're literally just electron density. They can be reshaped. And you end up with something that comes out to the same average density, or same average energy, sorry. And we put 1, 2, 3, 4 orbitals in, we get 4 orbitals back out. And it's made of an s and 3 p's. We're gonna kind of ignore the 2, like the n values on these, but it's an s and 3 p's, so these are called sp3 orbitals. Okay. And what the idea is that these orbitals are made of 75% p orbitals and 25% s orbitals, which makes sense. There's 4 total, and 1 of them's an s and 3 are p. But the idea is all of these are exactly the same. Okay? So they're the same shape, energy, they are evenly distributed. So rather than having an s orbital in the middle and then the 3 sets of perpendicular p orbitals on top, like I drew here, like you'd have an s in the middle and 3 p's, what you have are 4 orbitals that are not shaped like any of that. They're completely different. Hybrid orbitals, the shape generally looks approximately like a lopsided p orbital. So remember we said p orbitals have like 2 lobes and they're symmetrical around the center. These kind of have like a bigger lobe and like a little lobe. And there's like the center of your atom. Okay? And the idea is the unpaired electron lives here. And if you had 2 of these, like suppose you had 2 carbons connected together, or in this case we have CH4, this could connect to a hydrogen, which is an s orbital, and it could overlap like that. So this is the sp3 orbital, and this is the s orbital. Hydrogens, if you look at their Lewis structure, orbital diagram, don't really have anything to work with except an s, so they're an s no matter what. They don't get to be hybrid orbitals, but anything in the second row or below, pretty much anything but hydrogen, can form hybrid orbitals. Okay? I'm going to stop there and make this 2 videos, but this is the gist of how to start thinking about hybrid orbitals.